All right. So we're good, actually. When I do the recording, there's a purple bar that cuts off the top of this, and you can't, it looks like it's not actually recording correctly, but it's actually working just fine. So we'll continue. So let's look at some examples. Let's say we have this. Now, again, we could approach this two different ways. We can treat this as 25, 1/2 times 3, or this will be 25 to the 1/2 cubed, or the square root of 25 cubed, or we have 5 cubed and then 125. And that's going to be your answer. Now, you could do this the other way. And the other way, I think, is going to be much harder. We could treat this as 25, 3 times 1/2, or 25 cubed to the 1/2, or 25 cubed, we'll square root it. So 25 cubed $15,625, and then I'm going to use the square root key on my calculator, and I get 125. So again, depending on which way you go, this could be easy or hard or harder. So let's take a look at this one. Let's see. So I'm going to go with the root on this just because I think it's easier. So we could get 27 1/3 times 2 plus 16, and then we have 1/4 times 3, or 27 to the 1/3 squared plus 16 to the 1/4 cubed. Now, 27 to the 1/3 is the cube root of 27. So the cube root of 27 is 3. Now the fourth root of 16, 2 times 2 times 2 times 2. We need 4 2's. And so that means the fourth root of 16 is 2. And so now we can apply our exponents. 3 squared is 9. And then 2 cubed is 8. We add those together, we get 17. And that's going to be our answer. Now let's take a look at something else. Let's say we have this. Now, you can argue this how you want to do the convention. What they typically do in the text is we try to put the root on the outside. for this kind of question. So what this will become, xy to the 4 times 1/7. Or xy to the 4 all of that given the 1/7 power. Or we get the 7th root of xy to the 4. So again, typically on these, what they want you to do is have the root on the outside. So let's go the other direction. So, for example, square root of 7, that's really the 2 root of 7, or 7 to the 1/2. If we have something like this, well, again, we can write this as 13x, all of which has an exponent of 1/5. Now, let's say we have something like this. Well, again, we want to turn the root into a rational exponent. So this will have, this entire thing will have the exponent of, well, the rational exponent. So we have 11xy with a rational exponent of 1/2. Now we distribute this as an exponent. We'll get 11 xy 1/2 times 3, or 11 xy to the 3/2. All right. Now let's see here. Let's say we do one more like this. So 5th root of y squared. Again, let's make this into a rational exponent, and this whole thing will be on the inside. So we get 4x times y squared to the 1/5. We distribute this as an exponent. We'll get 4x times y 2 times 1/5, or 4x y to the 2/5. And that's going to be our answer. Now, the rest of these, we're going to start looking at some review of our rules of exponents. So, for example, for negative exponents, let's say we have something like this. Remember, with a negative exponent, we're going to flip. So if we have a to the minus n, this is a to the minus n over 1, then we flip it to get rid of the minus. Likewise, a minus down here, we flip it to get rid of the minus. And that's going to be it. So with this one, we're going to flip this. So we don't have to write the minus sign. And this is going to be the square root of 9, or 1/3. Now, let's say we have something like this. Now, again, we want to get rid of the minus sign. So that means we're going to flip this thing. So we can put it like this. Now we can distribute this exponent to this numerator and to that denominator. So that means cube root. Cube root of 8 is 2. Cube root of 125 is 5. Now, when you get this kind of an answer, there's a couple ways you can think of doing it. We can take this as 1 divided by 2/5, or you can give it that and make it a improper fraction by giving it a denominator of 1. Multiply across, and you get an answer of 5/2. Now, it's kind of a trick in mathematics that when you have something with one number divided by a fraction, what you can do as a shortcut is take this one number and multiply it by the reciprocal. And then I'll still give you 5/2. So any questions, let me know. I know this is recorded. Anyway. So let's take a look at one more. A couple more. Now again, we're going to flip this. And that lets us write it without the minus sign. And typically what we do in this case is we're going to, well, let's see, looking at the tag, what kind of answer are they looking for? In this one, they're going to let you just leave it like that. So you could just leave the answer like so. It is possible someone might want you to answer it like this. you could end up doing something like this. And then get, because this is what we've been doing in the past. But this seems to be good enough. So they're not going to have you drag all the way down here and extract that root. So let's look at one more. Now again, we're going to do some flipping, but in this case, we only need to flip the z to the negative 1/4. And to flip it, we're just going to flip it underneath the 7x. And that's going to be it. And again, we're not going to make this into a root. So that's just sort of a review of what we do with negative exponents. What we want to do now, we're going to continue reviewing the properties of exponents. So we're going to look at, for example, a to the n times a to the m, as long as the bases are the same, a to the n plus m. Likewise, a to the n over a to the m, a to the n minus m. Again, the bases are the same. And then this one, a to the n to the m, we've been doing this already. A to the n times n. Now we have distributive properties. AB to the n is a to the n, b to the n. Or if these already have exponents, we distribute the n, but as an exponent. So we get something like that. Same thing for the division. And if there's already exponents, and there you go. So we're going to bring back these rules with exponents. We're going to apply that to this, basically the same thing we do with rational exponents. So let's do some examples. Now again, these have the same base. So we're going to use the the sum of the exponents. Well, 2/3 plus 1/3 is 1. And that's just written conventionally as plane 5. So let's say we have something like this. So what we're going to get, same bases. So this is going to be 100 to the 3/4 minus 31 over 4. Double checking this, okay. So if we do that, we'll get 100 to, let's see, so they have the same denominator, so 3 minus 31. This will be minus 28 over 4, or 100 to the minus 7. Let me double check something. All right. So what that's going to give us is 1 over, we got to flip it, 100 to the 7th. Now 100 to the 7th is going to be quite a number, so I'm just going to leave it like this. Now let me take a look at this one. I'm going to double check. Because the textbook is giving me an answer of 10. And that doesn't seem right. So I'm not going to go with that. Subtract. Good. Flip. Yeah, that's going to be it. So that might be an error in the textbook. So if anything more about that comes along, I'll let you know. So let's say we have this. Now let's distribute the 1/3. We're going to distribute it just like we would any exponent, and we distribute it as an exponent. Again, we don't distribute it to multiply to 125. It's going to become an exponent of 125. So cube root of 125, that's what this means. This is x to the 3rd, y to the 2nd. Cube root of 125 is 5. And that's going to be your answer. So again, we use the exact same rules that we do for regular exponents. So there's another kind of simplification that we do. And that kind of simplification, so what we looked at before, recall this. The nth root of a to the n is the absolute value of a. And then for odd n, we're taking the odd root of something to an odd exponent. It's just regular a. And this one's a little confusing because if a was a negative number and we raise it to the nth power, we're going to get a positive number, assuming that n is even. And then we're going to ask, again, when we're dealing with even roots, we have this positive root and this negative root. This is insisting on the positive root of whatever is in here. So we'll get a positive number. Effectively, this becomes an absolute value for A. So if A was negative, it'll be taking the absolute value of that negative number A. So in this case, with odd, doesn't matter. It just pops right out. So we're going to make this one caveat. Assume A is greater than or equal to 0. Then we can say the nth root of A to the n equals A for even and odd n. So provided that what's on the inside is always positive to begin with, we can do this. We don't have to worry about that absolute value. So let's say we have something like this. The 10th root of x squared. So what we're going to do, we'll treat this as x squared to the 1 over 10. Again, the root here we're going to treat as a rational exponent. Multiply together, we get x to the 2 over 10. We can reduce that to x to the 1/5. And that's going to be our answer. So once again, we're going to treat this as a rational exponent for everything on the inside. So 27, A to the 12, to the 1/3. Distribute as an exponent. 27, 1/3, A to the 12 times 1/3. Excuse me. So this will be the cube root of 27, A to the 12 over 3, or 3 times A to the 4th, or 3 A to the 4th. Now let's do one like this. Again, we're going to treat this as a rational exponent for what's on the inside. We'll distribute the 6 as an exponent. So we'll get 2A to the 6/8. We can reduce that to 2A to 3/4. Let me see what kind of answer they want for the text here. So they want this one. They do want you to write this one in terms of a root. So once again, when in doubt, if they don't want the answer as a rational exponent, they want you to tease out the root. So that means we'll leave the 2a cubed times 1/4, or 2a cubed to the 4th. Oh, I'm going a little bit fast. Let me do this. To the 1/4. The 4th root of 2a cubed. Or the 4th root of 8a cubed. And that's going to be your answer. So sometimes the one answered like that. Now, let's take a look at another one. So one of the things you can do, and they don't really mention it explicitly in the text, but it's combining roots. Now, this is something that comes up from time to time. And let me show you how this works. Let's say we have this. So what you could do here is treat this as x to the 1/2 times y to the 1/2. And then you can act as if we had distributed that 1/2. And again, we had distributed it as an exponent. So it's xy to the 1/2. And then we can convert this back to a root to get this. So one of the advantages of using these exponents for roots, these rational exponents, is that you can use them to show that you can use multiplication to combine square root signs. Now this can get kind of fancy. So let's say we do something a little more complicated. Let's say we have this. Square root x over square root y. So what we could do here is, again, x to the 1/2, y to the 1/2. And then we can act as if we distributed the 1/2. Then we can turn this back into a root. This whole thing is under the square root. And so that's going to be our answer. So what you can do is you can use this, and let's see, we'll get to this in the next section. But in general, what you're going to get is the nth root of a times the nth root of b will be the nth root of a times b, provided that the roots match. They have to be the same root. Likewise, the nth root of a over the nth root of b, again, you can bring these together under the same nth root. So that being the case, That's a special case. And again, that's when the roots are all the same. Now we're going to look at some examples here when the roots are different. So let's say we have something like this. Now what we can do here, again, rational exponents. So what we could do, we can distribute this and distribute that as exponents. So 2 times a fourth is 1/2. And then we can, this is all multiplication, so it's all commutative, so we can switch orders around and put the a to the 1/3 over here, and then the b to the 1/4, then the b to the 1/3. And then we would add these together. Now, common denominator, say 6 for this one. And so that means we'll have multiply top and bottom by 3, or top and bottom by 3. Top and bottom by 2. Common denominator of 12. So multiply top and bottom by 3. Top and bottom by 4. Let's see, 7 12s. Well, let me see, what kind of answer are they looking for here? Check one thing. Okay, so this might seem kind of strange. In fact, it is going to be something we really haven't dealt with before. What we're going to try to do is extract a common root. Now, as you recall from when we had m divided by n, like 1,000 to the 2/3, we could take 1,000 to the 2/3, and we could break it up a little bit. We can do some of this, where we're taking a cube root, and then whatever that is, we're squaring it. Now, the problem we have here is that, well, the root, we see the root in the denominator. So if we want to extract a common root, we need to have a common denominator. Now we can make this into a 12 if we multiply by 2. So that's what we're going to do. Multiply top and bottom by 2. We'll get a to the 10 over 12, b to the 7 over 12. And what we can do next we can extract the 1 over 12. So what we can do is we can think of this as a reverse distribution, and this is one of our exponent rules, is that we would usually take the 1/12, distribute to here, and distribute to here. Distributing to here, we get 10 over 12. Distributing to here, we get 7 over 12, or 10 over 12 and 7 over 12. Well, now we're just going to go backwards and extract that 1 over 12 as an exponent. Now it can be a root. Now, again, for all these problems, we're assuming that A and B are all positive. Not just A, but B also, X, Y, everything here is going to be positive, all the variables. So we don't have to worry about any absolute values. Let's see. Oh, here's a good one. So let's say we have this. So how do you simplify this? Well, we can write this as a rational exponent. We can write this as a rational exponent. So on the inside, we have x to the 1/2. On the outside, we have a 1/4. So the next thing we can do, distribute that as an exponent. X to the 1/2 times 1/4. X to the 1/8. And that's going to be your answer. Let's see. Let's do this. So let's say we have something like this. Well, what we can do, we have different roots, so we can't combine them into one root, but we can rewrite them using rational exponents. And we'll distribute these as exponents. There we go. So now what we're going to do, we're going to use our subtraction rule. And again, because the roots weren't the same, we couldn't combine them into one root. So we're going to get A to the 3/4 minus 1/2, B to the 3/4 minus 1/2. And for this one, we would have to assume A and B are greater than 0. So we don't get division by 0. So this will be A to the 3/4 minus 2/4. Multiply top and bottom by 2, get the common denominator. B to the 3/4, again, 2/4. So what we get is A to the 1/4, B to the 1/4. Well, let me see what kind of answer they're looking for. We do want to extract a common root. So what we can do, we can extract or factor out as an exponent 1/4. And we take that 4th root and that's going to be your answer. So that's it for section 7.2. if you have any questions, let me know, and I'll get 7.3 out as soon as possible. We'll continue on. Looking at 7.3, this is where we're going to take into account where we do have the same roots in a product and in a quotient. And we'll do some work with that. We'll do some factoring, actually, because if you recall, I did mention that with roots, we do what's inside the root first. It acts like there's invisible parentheses, but that's not always. There is a little bit extra we can sometimes do, though we still have to mind the root. So we'll get to that in 7.3. Other than that, have a wonderful day.